Welcome to the second video in a 4-video series on sequences and series. This one is about series notation. And if you watched video 1, this one is a lot like the last one in the sense that there are no particular procedures or how-to kind of teaching moments here. The purpose of this video is just to get you the idea of what a series is and what kinds of notation and terminology we use when talking about series. The actual how do you solve the math problem situations come up in video 3 and 4. Let's start with what a series is. A series is basically a bunch of numbers added together. But more specifically, series are only interesting if the numbers you're adding form a pattern of some kind or are a meaningful sequence, is another way to say that. So look at these numbers and convince yourself that not only is this an addition problem, but it's an addition problem with a pattern. You can see that the terms are spaced out by 3, for example. This dot, dot, dot here, also known as an ellipsis, is the mathematical symbol for and so on. So this is not to be thought of as 2 plus 5 plus 11, 8 plus 11 plus 62. It's to be thought of as all the numbers in between added up, following that same pattern without us having to list those numbers. Now I worked this out and I got 672. And here's some more terminology here. We would call this thing a finite series, meaning it's not infinite. It's finite because it only has, I believe, 21 terms in it. It doesn't go on forever. We call this the series, and we call this the value of the series. It turns out we're not always interested in knowing the value of a series. We're often interested in knowing properties of it or expressing it in certain algebraic formats. But nonetheless, there's a finite series. Series don't have to be finite. They can be the opposite of that, infinite or never-ending. Here's an example of a never-ending series. This represents 10 plus 12 plus 14 plus 16 plus 18 plus 20 plus 22, and so on and so on and so on. We would say that because there's no end to this series, and because the numbers get bigger and bigger, that this series has either a value of infinity or that it's divergent, either of which really means it has no value at all. There's no way to add up an infinite number of numbers in most cases, especially when they're growing and growing. It doesn't mean anything. By contrast, though, here's another infinite series to which we will ascribe a value, and I'll show you what I mean by that. But before I do, first notice that these aren't just random numbers added together. I'll pause while you try to detect the pattern in the numbers. You may or may not have caught this, but notice that from here to here, the terms were cut in half. Half of 3 is 1.5, half of that is 0.75, and half of that is 0.375. And because you'll notice by the red arrow on the right end, because it says dot, 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 and there's no number after the ellipsis, that implies that this series is infinite and never-ending, and that the terms continue to follow the pattern that you see, which in this case is being cut in half from the previous one. Okay, well, it turns out we assign this series a value of 12. Well, what on earth does that mean? How could an infinite number of numbers add up to 12? Well, here's what mathematicians think on the matter. I've added a few extra terms here just to see a pattern. By the way, this is the same series as the one above. It's just that I've listed out about 7 or 8 terms here. Well, here's the idea, and let me try to convince you that this series has a value of 12. These first 2 terms in the series add up to 9. Okay, well, that's not what we're trying to do. We're trying to add up all infinitely many of them, whatever that means. But notice that the first 3 terms in the series adds up to 10 and a half. Each of these orange boxes, such as this one, is called a partial sum. Here's the fourth partial sum, meaning I'm adding up 4 terms. If you add those, it turns out you get 11.25. If you add the first 5 terms, you get this. Notice what's happening to the partial sums. If you add the first 6 terms, you get something bigger. And 7 terms gets you even a higher total. But notice the partial sum, or the total of the first certain number of terms, doesn't seem to be getting higher than 12. And if I want out another term, I still don't exceed 12. As a matter of fact, we'll talk more about this in video 4, but it turns out that if you were to continue to add more and more and more and more terms to this, and look at partial sums including those terms, you would never exceed 12. But not only would you never exceed 12, you could get as close to 12 if you like. I'll tell you what I mean by that. If I wanted to add enough terms in this series to get 11.99999, I could do that. I may have to go out hundreds or thousands of terms in the series to get to 11.999, but I could get there. If you pick any number under 12, I could find enough terms to exceed that, but I could never exceed 12. And for that reason, we call the value of this infinite series 12. Let's change topics to something called sigma notation. This is what we call sigma notation. Let's break this down vocabulary-wise. First of all, this funky-looking symbol here is a Greek capital sigma, also known as a summation or a sum symbol in mathematics. The number underneath it is called the lower limit, which is essentially the start. More on that in a minute. The number above the sigma is called the upper limit, which is where we'll stop. More on that in a minute. And the algebraic symbols to the right are called the summand. That's the name of everything. What does all this mean? What it means, well, first let's pronounce it. It's pronounced the sum as n goes from 2 to 5 of n squared plus 1. And the really important thing to focus on here is the n goes from 2 to 5. Because what we're essentially going to do in this summation, or sigma notation, is we're going to let n have all whole number values from 2 through 5. There's my start, and there's my end. Watch what I mean by that. So we're going to take n equals 2. We're going to plug in n equals 3. We're going to take n equals 4, and we're going to plug in n equals 5. We're going to plug in all 4 of these values to the summand. That's what n goes from 2 to 5 means. Now, if you want to pause in between each one of these, feel free to do so. I'm not going to explain the arithmetic in any great detail, but notice I plugged in 2 for n, did the algebra, plugged in 3 for n, did the algebra. Same for n equals 4, and same for n equals 5. So I've plugged in all numbers from 2 through 5 into this summand. And putting the algebra aside for a minute, let's focus on the final results. The results were 5, 10, 17, and 26. So now back to the sigma notation at the top. The sigma notation is instructing us to add these results together. They want us to add 5 plus 10 plus 17 plus 26. That, by the way, adds up to 58. And that is, in essence, the value of this sigma notation. Here's some vocabulary. This is called sigma notation. This, where each term is written out separately as an actual number, that's called expanded notation. And this is called the value of the series. All 3 of these are equivalent. They're just different ways of looking at the number 58. But here's a question to ponder. What if we were given a circumstance where instead of being given sigma notation, we were given expanded notation, and we were asked to work backwards to find sigma notation? Here's a new example, and we're going to challenge ourselves with just that. So given expanded notation, we're going to try to create a sigma notation expression, like the one we just saw a minute ago, that has this as its expanded notation. So I'm going to have to set up a sigma notation. Now notice I've used the letter N here just to match the previous problem. But notice there's no N's, letter N's in expanded notation. And so really there's nothing unique or special about the letter N. It could have been anything. Just to make the point that I don't have to use the letter N, watch the letter N, I'm going to change it to K for no particular reason. Although N and K are traditional letters to use in sigma notation, the point I'm making is it doesn't matter what letter you use. Now, here's the challenge. I need to create the sigma notation. Let's call this K equals 1. Let's call this the term that corresponds to K equals 2, or this the term that corresponds to 3, and this the term that corresponds to K equals 4, and so on. In other words, I need an algebraic expression where when I plug in K equals 1, 2, 3, and 4, I get 4, 7, 10, and 13, respectively. To rephrase that, to use the language of sequences, video 1, we could call this term 1, term 2, term 3, and term 4. And again, we need to find an algebraic expression that will produce those terms. And to find that algebraic expression, I'm going to set up a table where on the left side I put the K value or the term number value, 1, 2, 3, 4, and so on. And on the right side I put the term values 4, 7, 10, 13, and all the way down to 40. Now my challenge here is to come up with an algebraic expression to put as my summand that will match the function described in this table. And if you watched video 1, you may recall the phrase general term. So I need a general term that matches this sequence or this table. Well, what does that mean? That means I need an algebra formula that will turn 1 into 4, 2 into 7, 3 into 10, and will turn 4 into 13. Well, how am I going to go about doing that? Well, if you watched video 1, you may recall feeling that this was a point of contention because there was no thorough explanation given for how to come up with this. And I do promise you in video 3 that I'll give you a more algebraic way to come up with a function that matches a table, especially one of this kind. But in the meanwhile, I'm going to recommend that you hit pause on your video and try to determine, just through algebraic cleverness, what is the rule that turns 1, 2, 3, and 4 into 4, 7, 10, and 13. Hit pause and try it yourself. Okay, the rule I came up with was the loosely said times 3 add 1 rule. If you didn't come up with that, I'm going to invite you to pause the video again and convince yourself that the concept of multiplying by 3 and then adding 1 will get us from the left side of this table to the right. If you need to, hit pause and convince yourself of that. Okay, so now how do I express that rule as my general term or my summand of the sigma notation? Well, I'll express it as 3k plus 1 because k was the letter of choice for this problem. Now I have my summand. But I'm not done creating my sigma notation, am I? I still need the lower limit, and I will eventually need the upper limit for this summation. The lower limit is the first k value, or the k value corresponding to the first term. Well, that's going to be 1 because we chose to start this series with k equals 1 as our first term. But the upper limit is a little bit more challenging. For that, I need to know the k value that corresponds to the last term. I cannot put 40 as my upper limit. I have to put the k value that would lead to 40. Well, there's a few ways you can figure this out. One is you could just write out the whole table. And by write out the whole table, watch the right column, I mean write it all out in the sense of 4, 7, 10, 13, 16, 19, 22, and so on, all the way down to 40. If you do that and then use the left column to write out all the k values, you will eventually find out that the 13th term of this series is 40, also the last term of this series. You could also just count on your fingers and toes. There's lots of ways to figure out that 13 is the k value corresponding to 40. If you're not comfortable with the counting, you could always use algebra and set the general term equal to 40. After all, we want to know what value of k makes this 40. It makes sense to use this equation to do that. And if you did solve this equation, I won't show the work here, but you would in fact find out that k equals 13. That tells me that 13 is my upper limit, and now I have my sigma notation for the expanded notation that they gave me. And notice what I've done here is I have completed the challenge of turning expanded notation back into sigma notation. Very tricky. More on that in future videos. And one last thing to point out about this problem is that it turns out there are infinitely many ways to turn expanded notation into sigma notation. So you just saw me turn this into sigma notation and give an answer, but it's not the only answer. It turns out this is another answer here as well. And while I won't take the time to explain where exactly I got this, because it's a little bit beyond the scope of this video, it is worth noting as we leave this particular topic that these two sigma notations are both equivalent and equal to the expanded notation on the right. And of course, you might ask yourself, how can two different looking sigma notations lead to the same expanded notation? Well, if you're up to a challenge, it'll take you about 2 to 3 minutes, I invite you to hit pause on this video, work out the blue sigma notation on the bottom, and you will see that it is exactly equal to the expanded notation on the right, which is equal to the red or top sigma notation on the left. In fact, that all three of these are exactly the same series of numbers. And that concludes the second of 4 videos in this series.